Well, welcome everybody. My name is Chelsea Troy. Chelsea, like the neighborhood in New York, Troy, like Helen of Troy. Today I'm going to be talking to you about what counts as a programming language. Here, this is where I write about code at chelseatroy.com. And then I'm Hey Chelsea Troy on Twitter, Instagram, you name it. So if you want to find me, you can find me there. But I do want to give you a little bit of a warning before we start this talk because it's entitled What Counts as a Programming Language? But as I was developing this talk, I was researching different programming languages and domain-specific languages, and what I realized was that the theme that I found in comparing and contrasting these programming languages was in fact a broader concept that doesn't specifically apply only to what counts as a programming language. So it turns out that this is actually a talk about assumed context more than it's a talk about programming languages. But we are going to look at programming languages as an example of what I mean by assumed context, okay? But before we get into that, let me start the talk the way that you would expect a talk about programming languages to start. We're going to talk a little bit about some prior art. So I did the bare minimum when it comes to prior art, which is that I Googled what counts as a programming language in hopes that Google would tell me all the answers I needed to know to give you a talk about it. And I found a number of different answers, and what I put on this slide are a couple of the most inclusive ones. So according to Code Academy, a programming language comprises the tools we use to write instructions for computers to follow. Okay, we got a similar definition from good old Wikipedia. It's not a grade school 5-paragraph essay without a definition from Wikipedia, right? A programming language is a formal language comprising a set of instructions that produce various kinds of output. Now, these both sound like relatively inclusive definitions, right? Especially that last one, a formal language with a set of instructions that produce various kinds of output. That could be almost anything. That could include natural languages. It could include all kinds of different things. But in practice, the discussion about what counts as a programming language is not always such an inclusive one. Many professional programmers are not as inclusive as those definitions that we just talked about. And in having this discussion with professional programmers, I've heard a few different questions come up that might help us to determine what counts as a programming language theoretically. So I'm actually going to start at the top of this list. Does it have to be Turing complete? Does it have to be able to solve any of the problems that a Turing machine might be able to solve? Now in practice, this typically means, does it have conditionals? Can you go to different parts of the program from parts of the program? Turing completeness is something that I have heard used to rule out markdown languages as programming languages, but we will get there later. Let's look at some of these other questions. Does it have to be usable for solving a specific kind of problem? Now, this one we're going to get into a little bit more later in the talk, but for now, it seems that the things that we count as programming languages are those that we use to solve specific problems within the realm of software problems. We have other problems that we use different things for that are not programming languages according to our arbitrary definition of what that is. And like an example might be an end user application where people change things in the input and that kind of thing. Usually, whatever we're doing that with, we count that as a programming language. Then there's this other question, does it have to actually be used for solving that specific kind of problem? Like, in order to be a programming language, does it not only have to be usable for a certain thing, but also used for that specific thing? Because, for example, when we're teaching people programming languages, we often do so with things like a tic-tac-toe game written in the command line. Now, that type of application is valuable for learning how to use a programming language, but in that context, we're not really using the programming language for the thing that theoretically it has to be a programming language in order to be able to solve, because we can also solve how to do tic-tac-toe with 4 lines and a pencil. We don't count that as a programming language. And finally, does it have to have a compiler and or an interpreter? Now, here's what's interesting about this one. At first glance, this one sounds like it would be the strictest one, right? Has to have a compiler or an interpreter. It's not a programming language. Well, maybe. But at its core, what a compiler or an interpreter does is it takes a representation of data in one format and it transports it to another format that maybe we can use for something else. It turns our front-end syntax into an abstract syntax tree. But how is that fundamentally different than turning one natural language into another natural language? Is it different from turning CSV data into JSON? We don't necessarily think of that as a compiler or an interpreter, but fundamentally what it does is very similar, which means that this last point might really make the definition of a programming language more inclusive than we imagine. So those are some of the general questions that come up when you're talking with a bunch of programmers after work about this. The more specific questions might include something like this. Is a markup language a programming language? Maybe HTML or Markdown or XML or JSON, ways that we typically represent data for programming languages to consume. Now, I don't want to say that there is consensus on any of this because there isn't, but in general discourse, programmers tend to say that these things don't count as programming languages. And when you ask 3 different programmers for the reason, they'll come up with 4 to 5 different reasons why that's the case, and none of them are the same as each other, and I confess I find it a little suspicious that what counts as a programming language very often coincides with what dominant demographics are willing and able to write in the tech industry at that time. Programming languages once upon a time were not considered a technical and intellectual task back when women and underrepresented minorities were primarily responsible for executing them, and now they are. But that's a topic for a different talk, so I'm going to move on. How about a query language? Is that a programming language? So take SQL, for example. That's a query language that we use for relationally oriented databases. Or how about Cypher? This is a query language that we use for graph databases. Once again, no consensus on this question, but generally programmers tend to be more willing to think of query languages as programming languages. But once again, when you ask 3 programmers why, you come up with several different answers, none of which coincide with each other. So I want to take a step back here and ask, what is it that we're trying to describe? Why does it matter to us what counts as a programming language? What are we trying to figure out here? Because we said programming languages, but maybe some context is missing here. Now, by context, what I mean is the descriptors that characterize our specific situation. The place where I grew up is a context. The city that I live in is a context. The industry that I work in is a context. The type of software that I work on is a context. The language that I learned as I was growing up is a context. And it's important for us to recognize those descriptors because they characterize our perspective. All of those things about me characterize the way that I see everything. And to me, the way that I see things can be very difficult to separate from the truth because it is what I see as the truth. Now, perspective is especially important in software engineering, and here's why. Computer science is not like biology or astronomy or geology or physics or fluid dynamics because it is not a natural science where there exist properties that we are trying to figure out that we had no hand in making. Computer science is entirely human-made. We built it, which means that at every step from its inception, our perspectives played a role. There is no piece of computer science or software engineering that is devoid of context, because context informs the perspective with which all of it was built. All of it. And this is how that can bite us. When we are unaware of the context that we are in, we can accidentally mistake our specific case, our perspective, with an imaginary general case, an imaginary truth. Now, before we go back to programming languages, I want to explore this idea a little bit, because I get that it's a little abstract. So we're going to look at some context-specific ideas to make this clear. I want you to think about this statement for a second. Generally, it is better to optimize our code for legibility than for speed. How many folks in this talk today agree with that? Show of hands? A few, maybe? Fewer maybe than at some other conferences. I know we have some programming language designers in the crowd. Generally, it's better to optimize our code for legibility than for speed. You see the word there underlined, generally. What do we mean by generally? Well, the thing is that there is context here that gets lost in generally. Generally means in most cases, but it doesn't answer the question in which cases. Generally, it's better to optimize our code for legibility than for speed. Maybe when we're writing end user client applications, it's better to optimize our code for legibility than for speed. Maybe when we're writing open source applications that rely on multiple developers across the globe not communicating with each other synchronously, so that different developers must be able to understand the code that the first developer wrote, maybe then it's better. I recently implemented my very first interpreter. I was following the book Crafting Interpreters. It's by a guy named Bob Nistro. He is part of the team developing the Dart programming language at Google. And I was going through the beginning of the book, and we were lexing some stuff. We were looking at different tokens in the programming language, and I saw a giant case statement that we were supposed to implement, and I decided, you know what, I could do it better than this, because this isn't particularly legible, and we could make the hierarchy here much clearer with a tiered series of conditionals. And so that's exactly what I did. I refactored it, and I thought I was so smart. And I reached out to Bob, and I asked him, out of curiosity, why is it done with that case statement? Rather than tiered conditionals, it might be more legible. And he said he agreed. He said that the tiered conditionals were more legible, but the bottom line is that when you're writing a programming language, it's extremely important that the thing be fast, because you don't have to worry about the speed of looping over 14 keys and values in your Ruby app, in your Python app, in your Java app, because the people who wrote the compilers and interpreters for Ruby and Python and Java made them fast enough to give you the luxury to optimize for legibility rather than for speed, because they optimized for speed, so you don't have to do it if you're an end user client application developer. So let's look at another example. Generally, composition is preferable to inheritance. Common saying in object-oriented programming, functional programming too. Generally, composition is preferable to inheritance. What do we mean by that? Once again, we have this word generally. So I teach a class at the University of Chicago. It's called Mobile Software Development. We learn Android and iOS. Both of those frameworks rely heavily on having the client developer inherit from classes that are provided by Android and iOS. It actually makes those classes pretty hard to test, because Android and iOS handle the instantiation of those classes by themselves. You don't have to do it, which means that you have to use tricks and or import libraries in order to be able to instantiate classes in tests and do dependency injection, have control over the way that your classes work. You have to go around the framework in order to handle your instantiations yourself. Why do it that way? It makes it so hard to test. Why do it that way? Well, it turns out that when you're trying to make complex stuff happen in a device that big, size of my palm, it's really important to conserve memory, which means it's really important to conserve the number of objects that you have running at the same time. You have instantiated at the same time, you're keeping track of. And it's a lot to think about for a developer. And it would be very easy for an app to run out its sandbox and crash if the developer had to think about that. But in order to take some of that load away from the end user application developers, the designers of the Android and iOS frameworks elected to do it for us. They elected to put that behavior into the classes and have us extend from them. We have the luxury of preferring composition to inheritance because they used inheritance to solve problems that we no longer have to think about because they did that. And that brings us to this question, what does generally mean? And we agreed earlier, it means in most cases. But which cases? I understand that when someone is new to learning programming, we use generally to keep things simple for them. We don't want to expose them to all of the nuances and special use cases early on. It'll intimidate them. Nobody starts by writing a compiler. Nobody starts by writing the Android framework. Why would we confuse them like that? I agree. But when we are at the point of advancement in our technical understanding, that we are responsible for teaching other people, generally, blah, 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 at that point, we are responsible for knowing what we mean by generally. We are responsible for knowing what cases we are speaking for when we say generally. So now, let's return to the topic of programming languages. Python, JavaScript, Java, Kotlin, etc. are considered general programming languages. There's that word again, general. General programming languages, we say, differ from domain-specific programming languages, like Cypher, aforementioned Cypher, or RSpec, which gets described as a domain-specific language for writing tests in Ruby. Or how about regexes? These are described as a domain-specific language for parsing and understanding complex and varied, but ultimately similar text patterns. By the way, if you're interested in regexes, Betsy Habel does an excellent talk on the design of regexes and why they are so pervasive, and I highly recommend it. The point is that once again, we have this word general that we are comparing to domain-specific. Here's the thing. I'm not sure we know what we mean by general here. What if the general case is, in fact, specific to a domain, and we only think it's general instead of domain-specific because we consider its domain to be the default one, much like the way that we call a t-shirt a unisex t-shirt. That ain't no unisex t-shirt. It's just a men's t-shirt that we sell to men and women. And then we have women's t-shirts. Those are a special case. Really, we don't have a general case there. We have two specific cases. One of them gets treated as the default. What if we do that with programming languages too? So, Brett Victor talks about this on his blog. It's called Worry Dream. So I recommend taking a look. He talks about the default domain for programming languages. What do we mean when we say a general programming language? Maybe we're actually talking about a domain-specific programming language, but the domain, the default domain is end-user applications where the user can change something. We're not talking about static web pages because the programming community has decided HTML and CSS aren't programming languages, right? Now here's the thing. It's not really this end user application where users can change something. Maybe it's not really a default domain. It's just the one that has received the most attention. Now, why is this one the one that receives the most attention? That might be the topic for another talk, or maybe we'll talk about it in the questions portion, but for now, let's say, maybe it's a domain-specific case. And we have other domain-specific cases that it would make sense for us as general programming language designers and writers to pay more attention to. Take Alloy, for example. This is a domain-specific programming language. The domain in this case is structural verification. Help us figure out how our domain models need to be created, how they're going to interact with each other. It's helpful for checking that our assumptions about how our models interact with themselves and each other will work, and we can check those assumptions. Alloy then uses a SAT solver to determine whether those assumptions are true. Alloy, and another domain-specific programming language, TLA+, can be used to figure out data model issues that you might not see as a bug in your application until you're 17 steps down the line and some complicated corruption has happened in the data. But we're not prone to using Alloy and TLA+. We use general programming language rather than domain-specific ones. So instead of figuring out those problems ahead of time and writing a simple domain model that eliminates those problems, we've decided it's better to write an app, get 6 months down the line with 60,000 lines of code, have a weird bug that we can't figure out how to solve, write an issue about it, put a bunch of angry face emojis in there, come back to it every month or so when we see the issue, but never ultimately figure it out. That's not better. Right? Like, if we were prepared to take our general programming language knowledge and say, okay, we write these programming languages for end user applications, but what could we learn from Alloy or TLA+, or a similar domain-specific language about what it is that we are trying to do better? Let's look at another example. Modelica. Similar programming language in Simulex. These are domain-specific languages that are used for modeling physical systems, used frequently by mechanical engineers. Big user is Ford, General Motors, designing cars, figuring out how systems are going to work together. These types of programming languages are extremely effective at helping to determine how complex mechanical systems need to work together. Once again, getting complex systems to work together is something that our general programming language world generally thinks of as hard. What could we learn if we would promote programming languages like Modelica and Simulex in importance and figure out how our domain-specific end-user application programming languages could benefit from the lessons of mechanical engineering domain-specific programming languages? My favorite, Cypher. We already talked about Cypher twice, and the reason that I keep bringing it up is because I think it's fantastic. I love Cypher. I really like it as a query language. I think the thing that I like the most about Cypher is that Cypher queries very often look like little diagrams that describe exactly what it is you're trying to get out of the database. We have these nice round parentheses that indicate what our models are, and then we have these square brackets that indicate what our relationships are. And I just love that the query draws a little picture for you of what it is that you're trying to do. Now, my tenure in programming isn't as long as some of yours, I'm sure, but in my time, I have so far seen at least 3 attempts to create a diagrammatic programming method so that we could use general programming languages by drawing pictures. And you know, all 3 of those efforts that I have watched have failed. And so I'm forced to wonder, if we're willing to promote query languages like Cypher to the level of importance that we give general programming languages, what could we learn from Cypher about how to do this thing that we've been trying so hard to do in the languages we use for writing end-user applications? The point is that other domains exist, and paying attention to them can make us better at this programming thing. I want to know what we can learn from languages that we think of as domain-specific. And I think the only way we can do that is if we recognize them as siblings, not subordinate, to the programming languages that we write, because our languages are also domain-specific. They're just specific to a different domain. We talked about this question earlier. What separates converting CSVs into JSON format from parsing a high-level programming language to an abstract syntax tree? One operation might be more complicated than the other. Maybe not even prepared to take that as a given all the time. But this is the kind of thing where it's difficult to come up with an objective answer as to what separates them and what makes one subordinate to the other. And I'm not convinced that that's even a particularly productive conversation to have. Rather, there may be more value in learning to identify contexts and share information across contexts than in formalizing our understanding of the differences between domain-specific languages in two separate domains. Why does it matter what counts as a programming language? What matters is where can we find contexts where there might be transferable knowledge. You and I swim in a sea of context. And the thing about context is, it's very easy to not realize it's there. But we benefit from learning to do it because you can access a deeper and better connected understanding of programming languages, and maybe anything, but I'll stick to what I know, by learning to find the invisible context hidden in general statements. So how do we do that, right? Well, I got a couple ideas. I'll share 4 of them with you. First of all, I recommend asking yourself a question. What principles or ideas or best practices do you think of as always right or generally right? What strikes you as right or true? I recommend pulling out a notebook. Write down just 2 or 3 of these. You don't need more than that. 2 or 3 will already give you a ton of practice at identifying context that you didn't realize was there. All right, once we have those written down, let's look for the context. Maybe there's a context in which this is the case. You can look for the water around you. This thing that I think is true, it's based on my experiences doing X, Y, and Z. What's similar about X, Y, and Z? Were they all end-user applications? Were they all for a specific market? Did they all solve a similar problem? What did they have in common? That's a really strong clue as to what your context is. Once you have that context, you can go looking for contexts that are different from yours to better understand why your best practices work in your context. Whatever it is that X, Y, and Z had in common, go find an application that doesn't have that thing in common. See how it's different. Determine whether the things that you think are always true are still true there. Nothing demonstrates why something works better than an example where it doesn't work, right? So doing this also gives you a better understanding of how your best practices are working. And finally, And this is the thing I would love to see us do that's going to allow us to draw wisdom from Alloy and TLA Plus and Modelica and Simulex and Cypher. Go looking for similar context to yours. What can your tried and true approaches contribute to that similar context? But maybe more importantly for programmers, what can you learn from this similar context about what new things to try in your own context? Because when we learn to humble ourselves and understand our perspective and the fact that it differs from a universal truth, that gives us the opportunity to capitalize on other perspectives to build a better model of what the truth is and how we can find solutions for the problems that we face. Learning to see and understand and compare contexts will help us open doors as solutioneers that previously we couldn't not only open, we couldn't even see. Right? So with that, I'll open the floor to questions. Let me stop sharing my screen here. Did I stop? I think I stopped. All right.
All right. Thank you so much, Chelsie.
Thank you.
So our first question here is from Tig Williams.
Yeah, hi. Having put that question up there quite early on, somewhat naively, to give you context, my background was as a DBA. So my peers have almost never considered me a programmer because I've always worked in scripting. And I think from what you were saying, you're talking about looking at things that aren't traditionally considered a programming language, looking at the approaches we use and combining those. And I think from my programming career, that's what I've always done because I came from different contexts to the norm, if that makes sense. My start was engineering rather than programming, but I'm now in education, I'm now teaching, and I've always been picked up on the difference between the programming language and a scripting language, and a programming language has to be compiled and a scripting language interprets end of, and that's where we go. And I've rather naively always taken that as read. So could you sort of elaborate on that one for me and tear that wall down?
Sure. Well, the thing is that programming languages, to me, I think the idea is essentially that the thing that we think of as a general programming language and the things that we think of technical in general, to be honest with you, are moving targets. They're often arbitrary constructs that we make up according to who we want to have count as technical at a given time, who we don't want to have count as technical at a given time. In that way, they are not completely dissimilar to whiteness as an abstract concept. Who's white and who's not white has changed over the past 100, 200, 500 years according to social context and who the people in power wanted to also have in power or wanted to give power to at a given time. I don't particularly value definitions with normative judgments attached to them around what counts as technical. And I think that often that's what we end up having when we try to define something specifically as a programming language versus a scripting language versus a markup language versus a query language or something like that. I think a lot of times, maybe this isn't necessarily the intention, but the implication in a lot of those discussions is that one of them counts as real tech work. The other one does not count as real tech work. And I think that's garbage because ultimately all of them end up being necessary for us to do the things that we need to do to get the solutions to the people who hire and or need us to write whatever it is that we need to write. All of them are technical. All of them require technical knowledge. All of them require study. All of them have finicky bits. All of them have pieces of logic in them that are ultimately really brilliant. And I think that the distinction between the different categories is far less valuable than being able to take each one of them as a peer rather than a subordinate to any other one of them, and find out what we can learn from one and transfer to the other. I think that computer science is a young enough field that it is imperative for us to do that. We're only, I don't know, max 150 years old, with a lot of what we've done having happened in the last 50 years, and already we see ourselves repeating solutions that were already tried. We see GraphQL, which is extremely similar to a lot of the SOAP protocols that we saw in 1999, but people don't realize that those similarities are there all the time. I think it's extremely important that we learn from other solutions in order to build the things that we're building now, because if we don't, we waste a lot of effort redoing things, and we make ourselves look silly when we praise one solution and denigrate another one, and it turns out under the hood they are so similar. Does that make sense?
All right, we have another question from Tomas.
Cool.
I'm working on unmuting. Okay. This was the question I posted was very short because it was an immediate reaction. And I thought the point you were making about how these statements are often normative judgments was really nice. And I really like that. And I sort of, it's connected to what you said earlier in the talk about how computer science isn't scientific because we're not sort of looking at the real independently existing matter, and I'm sort of wondering if you would see that as another normative statement about what is scientific and what is not.
Mm-hmm. That's a really good question, and I think you're right that a normative judgment often gets attached to that. When we talk about whether computer science is a real science, when we talk about whether political science is a real science, or whether psychology is a real science, it's very common for there to be a normative judgment associated in that, wherein if we decide the answer is no, then that automatically proves that computer science or political science or psychology or what have you are less valuable, are subordinate to the natural sciences. But, you know, I live in the United States, and I think that the last 4 years in the United States have demonstrated to the world, anyone who wasn't already aware of this, that political science is in fact not subordinate to natural science insofar as that failure to study it can in fact wreak havoc and cause so much harm, because we're in a situation where we know that the climate is changing, and we know that the way that epidemiology works and the things that we need to do in order to stop an epidemic, we know those things. And in the end, we cannot even use those lessons because lessons in political science would provide the gateway for us to be able to do that, and it's not happening. And so I think you're right. I think that that normative judgment is absolutely there, and I think that I hesitate to use always, but I would say in my experience, the vast majority of the time, those normative judgments associated with categorizing fields of study do more harm than good.